On March 26, 2024, the Francis Scott Key Bridge in Baltimore, Maryland collapsed when it was struck by a container ship. To clear the wreckage of the bridge, highly trained divers had to get down in the twisted steel to pull chunks of bridge out of the water. But the water was so murky, they couldn't even see what they were doing. To guide the divers, the salvage team used state-of-the-art 3D sonar modeling of the wreckage. But the divers couldn't see the 3D maps while they were underwater, so a surface team had to instruct them, as if controlling a robot, telling it where to go and how to move.
I had multiple people on deck telling them, through their helmet what to do. So, move your arm left or right, pick up that object. They were working with the very best divers available, the most advanced underwater sensing technology available. I think that is a perfect example of a situation that needs an improvement in technology in this area.
The collapse closed the Port of Baltimore for 11 weeks, costing an estimated $15 million per day in economic impact. Technology that could speed up this recovery time could save millions, and not just in Baltimore. Undersea infrastructure carries power, resources, and data all over the world. Undersea cables form the backbone of the internet and our global banking system. Pipes and cables carry electricity, oil, and gas across bodies of water everywhere. That's why researchers at MIT Lincoln Laboratory are developing a new tool to help find and repair issues with undersea infrastructure, an autonomous robot dive buddy that identifies objects underwater even in zero visibility, guides divers to their work, and helps navigate in impossible conditions.
So autonomy for undersea vehicles and really even just maritime vehicles is very, very limited by the dynamic and harsh ocean environment. You go underwater, you're getting shoved around. You might not be able to even overcome the forces that are pushing you around. So you have very, very limited sensors, very, very limited mobility all the time.
You're almost in sensory deprivation, but you still have to do complex tasks. You may say something like, if you see a rock, go to the right. Well, but you don't necessarily even know what a rock looks like, because on one day it may be clearly a big thing sticking out of the mud. On another, it may be sort of this vague, murky shape. Either way, you still have to make a decision.
Even professional divers have a hard time navigating underwater. The standard technique is for divers to count their fin kicks. Imagine walking with your eyes closed in a snowstorm, counting your footsteps, and trying to hit a target. Inspiration for the project came from a Navy SEAL diver.
So our collaborator at MIT, Professor John Leonard, has been working on related problems of underwater navigation for a number of years now. Some of them have been inspired by a number of Navy divers that have come through his lab. Over the last few years, we've been working more and more with special operators, particularly in the Navy community, who have to deal with very, very challenging situations with extremely limited resources. I'm very familiar from my experience as a scuba diver of how difficult it is to work underwater. So I am very motivated to try to give our special operators better tools to work with.
The challenge was, how do you give a robot enough information that it can be a helpful dive buddy in this situation? So it can know its own location in the water, know the diver's location, be able to find objects, and then guide divers to whatever it finds. And how do you do that without traditional tech at your disposal? Underwater, autonomous vehicles can't access GPS, so they have to use an IMU, an inertial measurement unit, to calculate where they are by measuring their own movement, like a diver counting their kicks, but much more accurately. But these techniques are only so good without external data to help ground truth them, to correct for the forces of currents and waves. Other than that, the underwater robots rely on cameras. In dark, murky water, cameras can't see much. That's why most ocean vehicles are equipped with sonar. Sonar uses sound waves, which travel through water more quickly and clearly than light does, to sense an environment. But sonar images are hard to understand. Without experience with sonar, scans just look like a white blob on a dark background. For a robot to be able to identify objects using sonar, they'd need a lot of examples. We train models like this for optical cameras every day when we log into a website and have to solve a CAPTCHA. Picking out buses in an image helps teach models to identify buses. You're solving a problem that humans are good at and machines can't easily do yet. It's a perfect robot test and a perfect way to get more data. But CAPTCHA for sonar doesn't exist. There aren't big data sets of sonar images depicting broken undersea cables or hardware infrastructure for robots to learn from.
Something that we've run into is that sonar data sets aren't very large. There aren't that many of them. How do we learn the most from sonar images without being able to rely on extensive data sets? What I'm doing is using the optical images and the sonar images at the same time. So we can use strengths that models have to recognize things in optical images to be able to teach a model to recognize things in sonar images.
So when the optical camera algorithm saw something it recognized in an image, the sonar camera algorithm could learn to find the same object in its images.
This is our sonar. This is a camera. And what we're doing is this camera is taking images of things it sees, and then we're going to use an AI to train another AI to understand what the sonar is seeing. Because if you look at a sonar image, it's not clearly anything unless you have a lot of experience. So this will fit inside like that. This will go right here. They'll all connect up. And then what we'll do is we're going to drive this a couple meters off the bottom of the water and scan objects. And then we're going to use this to train that.
To start building a library of paired sonar and optical images, the team headed to the pool.
We went to the University of New Hampshire. There was the Sea Cadets competition where we just grabbed a couple of different objects. I swam side to side, back and forth, like in front of the sensor.
They also tested the robot's navigation abilities in the real world, launching off the Gulf Challenger and Gulf Surveyor at the University of New Hampshire, and off Coast Guard boats in Boston Harbor.
So after the pool, I was able to work on my algorithm, and I noticed that certain objects would turn out the best. And I wanted to go to a place that was outdoors, more real-world environment instead of a pool, but also had clear water so that an optical camera could see something.
In Eagle Harbor, Michigan and Lake Superior, they put the systems together: waypoint navigation, communication, and real-time object detection.
What I was testing was if my algorithm would run in real time. So I found some metal objects I thought would be good. I have a stock pot and a aluminum barbecue pan. And then we had people in the water. So we had our autonomous vehicle traversing its waypoints, going around looking near the objects. And then when it saw an object in the optical and automatically found that object in the sonar, then it would print something that I could look at and see that, yay, it worked, it found it. So that was working in real time, and I was very happy about that.
The field test in Michigan showed that the system works. The robot can recognize objects and sonar in real time and communicate with a diver holding a tablet. The next step is to enable live reactive navigation based on what the robot identifies in its sonar and optical images.
Yeah, so at Lincoln, our specialty is solving applied problems and really thinking through them all the way from the start to the finish. So we didn't just develop a new algorithm, we built the software and hardware, we integrated them into a mission-relevant vehicle, and we tested them in different scenarios that are similar to how they would be used in the real world. One of the big goals of the program was to have it something that we could actually hand to the special forces and they could use it tomorrow. I think we would like to be able to take the diver completely out of the equation. In the meantime, though, as long as we need to have humans in the loop in fixing things in these very extreme environments, we want them to have the best available tools to do that.